There are many, many different kinds of chemical compounds which, depending upon the pH, have different kinds of color. So one of those examples is phenolphthalein, and I'm going to talk about phenolphthalein and its detail in just a second. Notice here's this chemical compound, phenolphthalein. I don't want you to particularly know anything about this other than the fact that obviously it's a nice organic compound. I do want to let you know that phenolphthalein was actually found in X-Lax, which was one of the first famous laxatives that was sold over the counter. The active ingredient was phenolphthalein. You put this in your body and whoosh, there you go. The problem with it is it turns out that phenolphthalein was found out to cause cancer. And so they ended up pulling the phenolphthalein containing X-Lax off the shelves and replacing it with something softer and gentler. But for a while, in the 40s, 50s, 60s, 70s, 80s, you had issues. You bought yourself some X-Lax with some phenolphthalein in it, and your issues were gone almost immediately. Well, you can imagine how chemists approach this. Chemists have phenolphthalein sitting all over the laboratory, so if you were feeling like having a good time with your friend, when you were walking by them enjoying a cool beverage, you would go squirt. And in would go the phenolphthalein into their beverage, and the next thing you know, the real live 100% unadulterated phenolphthalein would be doing its thing. But that's just a nice story for how things used to work in the good old days for chemists. Back to what phenolphthalein does as an indicator. It turns out that at pHs that are acidic, this stuff is clear. When you put it in water, it looks like clear liquid. But if the pH of the system changes to basic, if it becomes basic, a proton ends up being removed in what is actually an acid-base chemistry reaction. Here's this HA, where the proton is sitting on top of the phenolphthalein, this weak acid, and as the proton is removed, we make a base, a weak base, which is pink. So we go from clear in acid to pink in base. Well, automatically, you see an incredible improvement for this reaction here to be able to determine the number of protons we had to start. What if I squirted in a phenolphthalein? There it is, with a proton sitting on it. There's a phenolphthalein with a proton sitting on it. So this solution is clear. It's just sort of hanging around in the background. I start adding hydroxides, one after another, 1, 2, 3, 4, 5. As we will learn, when those hydroxides come in, they are going to go after the strongest protons they can find. They're going to go after these strong acids right here. They will leave the hydrogen sitting on this phenolphthalein, the protein on this phenolphthalein, alone until every last one of these other protons is gone. Once I've added 8 hydroxides to the protons, I have a water solution. That water solution is pH 7. I'm going to add 1 more hydroxide now. Here comes that last hydroxide. It comes in there. It sees this proton here. It pulls it off, and it makes A-. It makes the weak basic form. But what's the pH of a weak base? Oh yeah, something greater than 7. Oh, but wait. That means then that I have gone from having a clear solution when I had only the 8 protons in there along with my weak acid, which was the indicator, to one molecule of hydroxide past it, a pink solution, because I have the base, the weak base present. That's a much better indication of whether or not my solution is acidic or basic. And it is exactly the way that we go about telling us when the moles of protons equals the moles of hydroxide.